and get back to gas laws. So, uh, there's a few more things we can do with our ideal gas law. One of which is we're going to be able to go ahead and take a look at reactions. We can take a look at standard conditions to see some properties of things, and we can talk about mixtures of gases as well. Um, so, when we're talking about the idea of reactions, it is helpful to standardize things a little bit, and then we'll talk about the context of reactions. We're going to see that we have something called standard temperature and pressure, or STP, which is defined as 0 degrees Celsius and 1 atmosphere. Um, Although, again, this definition did change in the 80s to represent the bar instead of the atmosphere. Um, by and large, we still use this one, mostly because we still use the universal gas constant that gives us atmospheres, right? We use 0.08206, and so that'll be atmospheres. And we're going to see that at the STP, 1 mole will occupy a certain volume, which is going to make things very easy for us to calculate if we're doing things at STP. And this, again, was designated so that experiments could be done relatively easily, standardizing two of the conditions such that we're going to be able to do calculations very easily. And so we're going to see that if we calculate the volume, let's see, it'll be nRT over P. So 1 mole, 0.08206 liter atmosphere Kelvin mole. And then we have 298.15 Kelvin over 1 atmosphere. We see that if we do this calculation, we get 22.4 liters. And so this is known as the molar volume of a gas at STP. And this is roughly, just so you have an idea, it's roughly about 1 cubic foot, thereabouts. So if you want to think about this in terms of American units, it's about a foot. It's about a foot, right? And make a cube out of it, and that'll be about this 22.4 liters. So just so you have an idea of how big a space that is. It's a little bit bigger than a cubic foot, but it's pretty close. And so this is the volume of 1 mole, which is why we call it molar volume, of a gas at STP. And remember, this kind of this volume applies for any gas. So it doesn't matter if it's xenon, methane, whatever, trichloroethane, whatever, some random gas you have. It will occupy 22.4 liters at STP, which makes these things very convenient for us if things are at STP. So at STP, 1 mole equals 22.4 liters. That's a conversion factor. So we can use this in calculations of things if we want to talk about volumes of gas. For example, let's say I have a carbonated beverage, and it says that there are 4.5 liters of gas, of CO2. We'll say CO2. The 4.5 liters of CO2 is inside. And that's actually like, we're talking like a soda can. So maybe a little bigger, 500 mLs or so, would have 4.5 liters of carbon dioxide. That's the carbonation, right? Um, and let's see, we can see if this were at STP, we can see how many moles that is. So for standardizing our pressure and temperature, we'll be able to figure this out. And well, it's as simple as using a conversion factor, right? 22.4 liters goes on the bottom, and then we have our 1 mole on top. I'm not even going to put any decimals because this is a defined quantity for us. CO2. And as always, I have forgotten my calculator, so bust out the phone. Let's go ahead and do this. 4.5 divided by 22.4, we get 0.2. That's convenient, I guess, with just two sig figs. So we have a fifth of a mole of gas there. So it's roughly 1 times 10 to the 23rd power, or 1 point whatever 25 or something like that. So yeah, good stuff. Relatively easy. We can do calculations with this for reactions as well. Here's one of our favorite equations that takes place with gases. At STP, how many grams of NH3 is produced by 80 liters of H2 in excess hydrogen? Well, we can do this. And again, STP is going to make this easy for us. But if we didn't have it at STP, we'll take a look at this at different temperatures as well. So we have 80 liters of hydrogen turning into grams of ammonia. So we have our unit plan. Looks like we're going, since we know this, we know we have to go moles to moles somewhere in here, right? That's always how we go through these things. And in fact, we know how to go from liters to moles at STP, and we know how to go from moles to grams. That's molar mass, right? So we can just do this calculation. We know this is the molar volume, this is the molar mass, and this is the reaction coefficients, right? I told you, all this math is just unit conversion. That's all it ever was. There's your, what's it, the astronaut meme, right? Always has been. So let's go ahead and do this. So we have 80 liters of hydrogen. We have excess nitrogen, so we don't have to do this calculation twice. It's telling us we have a limiting reactant of hydrogen. We know that there's 22.4 liters in 1 mole of hydrogen. We have our reaction coefficients, 3 and 2. Those reaction coefficients are from our balanced equation. And then we have our molar mass, which for ammonia is 17.034, I believe, something like that. And then 1 mole ammonia. Do this calculation on your phone, of course. 80 divided by 22.4 times 2/3 times 17.034, and we get 40 point, how many, 6 grams of ammonia. So we're able to figure this out. The standard, just another unit conversion we're throwing in here. And we're going to see that if we're not at STP, we're going to have to use the ideal gas law. So let's say we do the same thing. We have 80 liters of H2 at 30 degrees Celsius and 0.942 atmospheres. So we're going to see what happens here instead. How many grams? And I'm going to again note that excess nitrogen just to make this easier for us. So since we don't have the STP, we're going to still have the same unit plan. We still have liters of hydrogen going to moles of hydrogen, going to moles of ammonia, going to grams of ammonia. Our unit plan is still the same. The only thing is our conversion factor for the first part will change. For here now, instead of using the molar volume because we're not at STP, we just have to use the ideal gas law. So we just need to multiply the pressure volume over the constant times temperature, and then we'll end up with moles of H2. Here again, we still have our reaction coefficients and molar mass. That part is not changing. The only thing that changes when we're not at STP is our first conversion. So let's go ahead and do it. As always, I would recommend pausing the video and trying it yourself, and we'll see what we get. So if we need to do PV over RT, that'll give us moles. So our pressure is 0.942. Volume is 80. R. And yes, you must put your entire gas, all those units there. And then we have with temperature, which I should just, I'm going to cheat and just add 273.15 to the Celsius. Just remember that we can't use the Celsius directly. All right, so that's our moles of hydrogen. And so now we just need to do the rest. So we need to do our reaction coefficients, which is 3 moles of hydrogen to 2 moles of ammonia. And then our molar mass. We'll get this. So remember that this whole blob here, that's moles of hydrogen, right? So because that's our volume of hydrogen that we have. And we have our other two conditions, the pressure and the temperature. So this blob is just moles of hydrogen. And so moles of hydrogen will cancel in our next factor there. So we'll still be okay. All right, so let's take a look. Let's do this. So 0.942 times 80 divided by 0.08206 divided by 303.15 times 2 divided by 3 times 17.034. This time we get 34.4 grams of ammonia. All right, and so we can also think about, does this answer make sense given our last answer? When we had higher pressure and lower temperature, we had a higher mass of ammonia that's produced, right? But at this higher temperature and lower pressure, if we think higher temperature, how does that affect volume? Higher temperature means that a gas will expand, right? V and T are over each other. So as temperature goes up, volume goes up. And since pressure and volume are inversely related, we know as pressure goes down, volume goes up. So 80 liters right here is actually less moles of gas to begin with because our gas has been expanded by the higher temperature and by the lower pressure. Both of those cause the gas to expand. And so as a result, this 80 liters is actually less gas than the 80 liters was previously. So it makes sense that if we have less gas, even though it's occupying the same space, we're going to have a lower mass produced in our reaction. All right, and so if we want to think about stoichiometry again, yes, we have now quite a few things we can do. We can do grams using the molar mass. We can do liters of solution. Remember, that's molarity. It's molarity. That's molar mass. And now we have our ideal gas law. And this would be pressure, volume, or temperature of gas B. So, and it would be duplicated on A, right? I'll go ahead and write this. We can go in between all of these things. So we have liters of solution A, and then we can also have grams of A, which is the molar mass, the molarity. So we have all these things we can do stoichiometry wise. So we can start at what we did in this last case with the ammonia. We started here, we then go to moles, we went to moles, and then we went to grams. So we went zigzagged up this chart. I could start with liters of solution. We go through moles, and then I could ask for the pressure of a gas or something. So I can start anywhere at A, at mass, at volume of a solution, or at pressure, volume, or temperature of a gas. I can start with any of those three because we know how to get moles from all three of those quantities. We have our conversion factors: molar mass, molarity, and the ideal gas law. Those are all our conversion factors. And remember, it simplifies the ideal gas law if you have it at STP, but you can always do the gas law. And then on the other side, I can get my answer in grams, liters of solution, or atmospheres, liters, or Kelvin of a gas. So I can go anywhere I want in this sort of graph here. All right, so whichever path we end up needing to take, don't forget the last stuff. We can still go grams to grams. That's just this path: grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. We can do that still. That's just stoichiometry. All of this is. So don't forget the last stuff from chapter like 3 or 4. Even though we're in chapter 10 now, it's still important that we remember all these things. So we're just adding on to our knowledge here. All right, so you'll see equations and that sort of thing on your homework. Alrighty, any questions so far? If not, we can move on. Okay. Great. So what we can do is we'll move on to talking about mixtures of gases. And with mixtures of gases, we're going to see that they are just going to very little. There will be a little bit different calculations that we have to do. All of our things will still apply. We remember that all gases kind of behave the same way, as we say, ideally. And we can talk about the total mixture of the gas together. So we're going to see that with a mixture, we see that gases behave, we kind of say different gases. I'm going to say the same in quotation marks because we're going to see later on that certain gases, as molar mass increases and all that, we're going to see that we start having deviations from ideal behavior. So in an ideal situation, gases all behave exactly the same way. And all gases are soluble in all other gases. That's the other part of this. So methane and oxygen, you can put them together. They're not going to not dissolve or something. Um, so because they're so far apart, they're not going to interact anyway. So all gas mixtures will be completely homogeneous if we have them in a container for a long enough time. So with these assumptions, we're going to see that for a mixture, let's say we have, here's our container, here's the container again, and here is the same container a third time. Let's say these are the same container, which means that volume and temperature and pressure, well, let's say not pressure, let's say volume and temperature are the same. So they all have the same volume, they all have the same temperature, right? Because these are the same container. And one container, like we'll say we'll fill it with gas that's blue. So I've put 6 moles of that gas in here, and I'm going to just put 3 moles of this purple gas. Let's say this is, we want to think about the pressure contributed by the blue gas happens to be 1 atmosphere. We're going to see that with this, I can also say that this one's just 0.5. I'm just arbitrarily giving these numbers. And let's say that in this, we're going to make it real easy. I have 6 moles of gas. And in this other one, I have 3 moles of gas. And hopefully we understand the relationship between pressure and moles, right? The more moles we have, the more pressure we have. So if I've doubled the moles, so say, purple, I have 3 moles and 0.5 atmospheres. If I double the moles, I'm going to double the pressure, right? Because they're going to hit twice as often because there's twice as many particles in there. We're going to see that if I mix these together, we're going to see that if we were to measure the pressure for this would be 1.5 atmospheres. 2 decimal points. Remember that we can measure pressure relatively easily. And so we're going to see that the pressure of these gases uh, would just be proportional to the number of moles that they have. So in a mixture, the total pressure includes all gases. However, the pressure exerted, I'm going to just move this down a little bit, by a single gas, aka the partial pressure, is proportional to the moles of that gas. And so if we think here, we have, I'm going to make this vertical, we have 1.5 atmospheres in our third container. And so we can measure the total pressure, and that includes all of the gases that are within that. Like, for example, the air, which has pressure on us right now, is made of nitrogen, oxygen, CO2, water, methane, all sorts of gases, argon. Um, with a mixture, like air, each gas contributes a pressure called a partial pressure. So right now I have nitrogen hitting me, so nitrogen exerts pressure. Oxygen is hitting me, argon is hitting me, CO2 is hitting me. All of those gases are hitting me right now. Or in the case here, we have our mixture here. We have our purple and blue dots. Those are the gas molecules in there. Um, and we're going to see that because the purple part is 1/3 of the mixture, right? We have 9 total moles in our third container. And if 3 moles of that are purple and our total pressure is 1.5, we have 1/3 of our gas is purple. And so therefore the partial pressure of the purple gas is 1/3 of the total pressure, or in this case 0.5 atm. And it's pretty easy to see, right? If we have 1 atmosphere of blue gas and half an atmosphere of purple gas, put those together, we now have 1.5 atmospheres of our mixture. But we can still talk about how each gas is contributing. Because once we know the pressure of one gas, we can do all of these ideal gas calculations for it. And so we'll see that how this works. Okay, so this comes down to what's called Dalton's law. And it's described as saying that the total pressure of a system is the sum of all the partial pressures. And so we see that partial pressure of purple is 0.5, partial pressure of blue is 1.5. Add them together, poof, we have 1.5. So kind of, I mean, to say that that's the total pressure is equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, all the way, however many gases you have. They each exert their own pressure. But it's a little bit less useful to talk about it this way. I mean, that's all well and good, but it's better to say that our total pressure, or rather our partial pressure, is simply proportional to what's called our, or here, we'll just say this. We're going to see x of A, x we'll define in a second here, times the total pressure. This is going to be a better way for us to describe this. We can talk about it in terms of the first two equations there, but they're a little less useful for calculating things. And we're going to say that x is the what's called the mole fraction. And mole fraction is simply your moles of A over your total moles. So the partial pressure of your gas A is related to the mole fraction, how big, like what proportion of your gas is one, of your mixture is one gas, times the total pressure. And let's take a look at this in terms of our purple and blue equation. We saw that the partial pressure of the purple gas would be the mole fraction that's purple times the total pressure. And if we look back to our actual numbers, our purple gas we had 3 moles, and blue gas we had 6 moles, meaning that altogether we have 9 moles of gas here. So that's going to be 3 moles over 3 moles plus 6 moles. That's our total moles for the system, times 1.5 atmospheres. And so if we do that, we see it's 1 over 3 times 1.5, which is 0.5 atmospheres. So in this case, we have our 9 moles of gas all together. That 9 moles of gas is 1.5 atmospheres. And 3 moles of that 9 moles is purple. The 1/3 of the gas mixture is purple gas. And so that purple gas contributes 1/3 of the total pressure. And so that purple gas is 0.5 atmospheres. All right, so we're going to see that this is not a terribly crazy idea. Um, but it's important that we do this when we talk about um, experimental considerations. Because very often we're going to have water as part of our environment. And when we have water nearby, that water contributes a pressure. And so when we're doing experiments, we often have to consider the partial pressure of water involved in an experiment. So let's take a look at vapor pressure of water messing with our system. And I should have, this is Graham's law. Where's partial pressure of water? Okay. Um, where is a good example for this? Um, I thought I would have an example, but I lied. So we'll just do one. So let's say that we'll take a look at the purpose of all this stuff in just a second here. So when gases are collected over water, this will be present in the let's see the produced volume of gas. And the reason for that is because often, in order to actually do these sorts of experiments, you do them over water. Because water is going to basically prevent other gases from coming in. So if we want to see how much gas is produced by a reaction, we do that reaction underwater. And so how that looks is you have a tank of water, you have a tube. It's kind of going to look like our barometer, but that tube is fully filled with water. So in the case of the barometer, it was filled with nothing, right? It was a vacuum. But this case is full of water. And so as our reaction happens, draw this again. We're going to see that our reaction here, which is this purple thing, it's going to start making bubbles come up because, right, bubbles go up in water. And eventually we're going to start pushing the water out, right? And the bubbles will start rising, and we'll end up trapping those bubbles there. And then when the reaction is done, this device is called a eudiometer, by the way. The fancy term for this thing. When the reaction is done, now our water level is down here. So all that purple gas has filled up the top part of this. So all of this would be purple gas, but there's also water vapor. That's what I'm trying to say. So this here this volume. So these have measurements on them. So they have little measurement or markers to indicate the volume. So say this is a 50 ml eudiometer. Maybe we've produced 30 mLs of gas or something. Um, and so we can measure that volume. We have graduations on there. We have a way to measure that volume. And unfortunately, because it's done over water, that means water vapor is also present. So we always have water vapor present um, in here. Because we know water evaporates, right? Even though it's not necessarily, 100 degrees, it doesn't have to be boiling. We know water will evaporate below that. And this is something that we're going to see when we talk about kinetic molecular theory in a little bit. The reason for this is, but there will always be some water vapor present. And the amount of that depends on the temperature. And so the water vapor depends on the temperature and pressure. So the amount of water vapor that's present. And so we have, if we flip over to Discord real quick, I should have this in our extra resources. I hope. Yeah. Okay, so let me switch the screen over here real quick. So yes, in Discord here in our handy dandy area, we have a water vapor pressure table. So this is going to show us at what temperature how much water vapor pressure we have present in our system. And so we're going to see that I'm going to write a few things out and we're going to look at this chart. So let's say we're conducting a reaction at 23.5 degrees Celsius. Was it 23.5 degrees Celsius? The vapor pressure of water is 21.7 millimeters of mercury. These are standard values that people have calculated. And since we're here later, we're going to see later on we're going to need this table as well. This is going to be adjusting for different gases when we talk about deviation from ideal behavior. So when we talk about real gases as opposed to ideal ones. But we'll get there later. So let's say we're conducting a reaction at 23.5 degrees Celsius and we're collecting the gas over water. So let's say we have we're going to take some magnesium. Milligrams of magnesium is placed in excess HCl in a eudiometer to collect over water. The total pressure, or rather atmospheric pressure, which will be our total pressure when we're doing an experiment like this. Let's say today it happens to be 754.2 millimeters of mercury. And we have our temperature already. And let's say that we observed that we got 58.9 ml of gas was produced. We can see how many moles of hydrogen would be present in that. So first things first, right? We should know the equation for what we're doing. Magnesium and HCl is collected over water. So we have that magnesium plus HCl. Hopefully we are able to predict that this is a single replacement reaction. So balancing, we get that. We notice we produce a gas, of course, because we're doing gas laws. It would make sense, right? We know the moles of magnesium that we're placing in there, right? And so we will have a theoretical yield here. And since I'm making up these numbers, we may totally have messed this up, but we'll see. We're going to see that we can calculate the moles of gas in two ways. We can use stoichiometry, but stoichiometry may here. Let's rephrase the question because I think it'll be easier for us to understand. What is the percent yield for this? And again, we may end up with a number over 100% because I just made these numbers up, but we'll see. We'll see. So we know we can calculate the moles, the theoretical yield, by taking our milligrams of magnesium and reacting them, right? We can figure out the moles of gas produced, theoretically. However, we have some actual values here. We actually collected 58.9 mLs of gas. But we know some of that gas is going to be water vapor. All right, so we have to figure out how much of that is going to actually be um, hydrogen gas as well. So we will want to do it this way. So we're going to see that our milligrams of magnesium will give us our theoretical yield. But our actual yield is experimental, right? And that's going to be what we have from our volume. And remember that percent yield is actual over theoretical divided by or times 100, right? So we can do that. Let's go ahead and do the magnesium first because that's the easy one. And say, we've got 82.2 milligrams of magnesium times magnesium's atomic mass is, got my periodic table here, 24.3. Oh, we have to actually convert to grams first, don't we? Definitely do that. Don't forget your metric stuff. We have, what did I say, 24.3 grams, 1 mole. We have a 1-to-1 relationship. So we have 1 mole of magnesium, 1 mole of hydrogen. So our theoretical amount of moles that we'll get out here will be, let's see, 82.2 divided by 1,000, which is the same thing as times 10 to the negative third, right? Divided by 24.3, and that's it. So our moles here, we're looking at 0.0033827 mole, and a 3 sig figs for that. So that's our theoretical yield. If we want to do our actual yield, we have to take a look at uh, that actually measured value. So the pressure, remember that a barometer works by having the pressure inside the tube equal to the pressure outside the tube, right? Because that's how a barometer measures temperature. We measure it against gravity. So if the pressure outside is 754.2, that means the pressure inside must also be 754.2 millimeters of mercury. That's our total pressure inside the tube as well as atmospheric pressure. So when you're doing these, those two are the same. Otherwise, we would push more. If we had a higher pressure, we would push more water out of our tube, increasing our volume. So just accept it, I suppose. The pressure outside and the pressure inside are the same. Pressure of the atmosphere is pushing up. We have the pressure of the gas pushing down, and that's equal to the atmospheric pressure. Right? Otherwise, we would end up pushing more water out. If we have a stronger thing, if they're both pushing equally, the water doesn't move. right? If I'm pushing things equally, if I'm pushing my hands together equally, my hands don't move. But if one of them is stronger than the other, then it's going to move things along, right? So that water level there where I have the arrow pointing to udiometer, that water level is there because the pressures are equal to each other. As we produce more gas, we produce more pressure that pushes the water level down. And so we end up having a larger volume at the end. So the pressure of the gas is equal to the atmospheric pressure. All right, so we have a volume, we have a temperature, we have a pressure. But this is a mixture of gases. It's a mixture, so we can't use that pressure directly. We know that the pressure of the atmosphere is equal to the pressure of our mixture, which is going to be equal to the pressure of hydrogen plus the pressure of water. That's our mixture. It's hydrogen gas and water vapor, both of those as gases. And so we have 754.2 millimeters of mercury is equal to our pressure of hydrogen plus our water vapor pressure. And that we're going to have to get from the table. And I had written that down here. It's 21.7 millimeters of mercury at this temperature. This value is from the table. And so that number is from our pressure table. So that means of this mixture, the pressure of hydrogen will be equal to 754.2 minus 21.7, which is 732.5 millimeters of mercury. All right, and so that pressure comes from hydrogen only, which means if we plug this into the gas law, then we're only solving for moles of hydrogen. Let's take a look at how that looks. We can solve for the total moles of the system by looking at the total pressure over RT, or we can look at the moles of a particular component of a mixture, whatever that happens to be, gas A, by looking at the partial pressure of gas A. So the total moles and the total pressure work out. And remember, if it's a single gas, these are the same, right? Because all of the pressure is contributed by one gas. But in a mixture, we have to use the partial pressure instead. That's the partial pressure of gas A, and that will be the moles of gas A. And so in here, this was our total pressure, 754.2. However, our partial pressure of hydrogen is 732 because that's all that part is contributing. Because in reality, the water vapor is also adding some pressure to our system. So we have to correct that by using this idea. So now that we've figured out the partial pressure of hydrogen, we can say, well, the moles of hydrogen would be the partial pressure of hydrogen times the volume over RT. Right? Volume and temperature are the same for your mixture. So water vapor is going to be at 23.5 degrees C, and it's going to take up 58.9 mLs. Those are the same for water as it is for hydrogen. The pressure and the moles are what change for mixtures. So for us, we can say, well, actually, we've got to do some adjustment first. We see that we have 732.5 millimeters of mercury. We're going to need to convert that to atmospheres, right? So we have 760 millimeters of mercury, 1 atmosphere. So doing that, 732.5 divided by 760, 0.9638. And this is with 4 sig figs. So let's actually take one more decimal point just so we keep rounding errors to a minimum. That's the atmospheres. The temperature was 23.5 degrees Celsius, so we need to convert that to Kelvin. 23.5 plus 273.15, 296, well, 296.65, and that's with that far, Kelvin. And then, of course, our liters would be 0.0589. Remember, milliliters to liters, that's something you should be able to do in your head at this point. Ready? So, let's go ahead and do this. So, the moles of hydrogen would be equal to our pressure of hydrogen. I'll be good and write my units. The volume, 0.0589 liters. We, of course, have our ideal gas constant. And then the temperature was 296.65. And so we're going to end up with 3 sig figs for this number. And let's go ahead and figure it out. So 0.963816 times 0.0589 divided by 0.08206 divided by 296.65. We get 0.002332, which is going to round to 3 sig figs, and that'll be our moles of hydrogen, which means, thank goodness, we're going to end up with a percent yield that's lower than the theoretical, which is our actual is lower than theoretical, which is a good thing. All right, it's something that makes sense. So all this work was to figure out the percent yield of this reaction, right? So in actuality, we got 0.0023. In theoretically, we got 0.0033. So luckily, we have found here that we did not actually produce as much as we wanted or thought we could. And so our percent yield is the actual yield over the theoretical, which is 0.002332 moles over 0.0033, I forgot the rest of the number, sorry, 827. Okay, so take this number divided by 0.00333827, and so we got that this reaction was 68.9% yield. Fun. So, look at all the stuff we can do with this. We have now talked about it in terms of reactions. We've talked about it now in terms of experiments. So remember, if you just use the entire pressure, you're going to see that you're going to get the wrong answer, because if you don't take into consideration that some of this partial pressure is just from the water, then you're going to end up with the wrong answer. So reality has that this is going to be a mixture that's produced. It's not pure hydrogen gas. There will be a small amount of water present there, and that small amount of water will still have an impact on our calculations. So the new stuff here is that we had to adjust from our total pressure, we had to subtract the pressure contributed by the unwanted gas, the gas that we didn't want to worry about calculating. And so in that case, that's the water. So anytime you see you're going to have something collected over water, that means that you have to deal with the partial pressure of water there. All right. Cool. Any questions on this? So thankfully, this is where I want to call it today, because we have 3 more weeks, I think. Let's check. We have Wednesday, and then we have Monday. I'm sorry, we have Thursday, we have Tuesday next week, we have Tuesday and Thursday, so we have 5 more lessons. We're going to see that we'll finish the gases on Thursday, and then we will start talking about intermolecular forces on Thursday. We'll continue that on next Tuesday. I'll probably have another video for you. I'll probably just record a separate one as well next week, just because it is online. I can do that, and then the week after that, we'll finish up with the liquids and solids, which are much easier. There's no exam specifically on these topics, but they are going to be present in more concentration on your final exam. So, like the gases, liquids, and solids that are our last 3 chapters of the semester here will be the kind of the bigger parts of your final. All right, so there's not a specific exam on them. All right, so we'll end here today. We will finish off gases next time, just a little bit left. And then we'll start talking about intermolecular forces. And then next week we'll talk about liquids. The week after we'll talk about solids. And that's it. And then we're done. So just a few more weeks. Alrighty, so that's it. And take care, enjoy, rest nicely, and you can get started on your gas homework. We have just kind of a little bit left. We're going to talk about kinetic molecular theory. We're going to talk about effusion and diffusion, and then we're going to talk about real behavior of gases. So I want, since this is a lot of material here, I want to just leave this aside, and then we'll come back to gases next time. All right, cool. Enjoy.